Good day, everyone. Welcome to another video lecture series for integral calculus. Okay, for today's video lecture series, we will be dealing with the topic integrals involving transcendental functions. Okay, so for today's objectives, we will be having we should be able to solve for the indefinite integral of the tangent, the cotangent, the cosecant functions. Okay, so next we should be able to express integrals of exponential and logarithmic functions and evaluate integrals yielding inverse trigonometric, hyperbolic, and inverse hyperbolic functions. Okay, so let's start with the first objective wherein we be getting the indefinite integrals, or the second objective where we have to express integrals of exponential and logarithmic functions, and later on we will be using these ideas for integrating exponential and logarithmic functions in getting the indefinite integrals of the tangent, the cotangent, the secant, and the cosecant. Okay, so this topic under in integrals involving transcendental functions, this is a part of this is only a part of very lengthy discussion on integral calculus regarding techniques of integration. Okay, so probably we could start off with a few examples just to recall some basic concepts that we have already discussed during our early video lectures. Okay, so let's have example number one just to recall a few concepts. Okay, so for example number one, we have here ln of x over x plus 1. So what is asked here is that you are asked to get the derivative of ln of x over x plus 1. Okay, so try to recall in your differential calculus that when you have the basic form of ln of x, ln of say ln of y, the derivative of an of the natural logarithmic form to of a given variable is one. For example, x. Derivative of ln of x is ln of x derivative of x. Okay, so just to illustrate, this is the basic formula for the derivative of ln of x, that is dx over x, or 1 over x derivative of x. Now it is important in our initial review to review the basic derivatives for the natural logarithm and the exponential functions. It is because the basic ideas for getting the integral of a given function is simply the reverse of the reverse of the process of getting the derivative. Okay, so let's proceed. Now, what is given here is not a single variable, but is an expression or a fraction, an expression which is of fraction form. So, what happens is one of the few techniques that we could use is the chain rule in doing our derivative. So you could do this on your own if you have your pen and paper with you. What we could do here is to represent x over x plus 1 as u. So doing that, you have ln of x over x plus 1, let u equal to x over x plus 1. Now, the next step is to get the derivative of u. Now, since this is our u, our representation of u, and this is in quotient form, therefore, in order to get the derivative of this function in quotient form, we make use, or we employ the process of getting the derivative of a quotient. Now, this part of the process of getting the derivative of a quotient, this is one of the basic techniques in getting the derivative of a function uh, you need to recall this in your previous notes on differential calculus, particularly on the topics of getting the uh, derivative of a quotient, derivative of a product. Okay, so as from now, what we can do is to simply recall the form of the derivative of a quotient. If you have, for example, the quotient is of the form, say, a over b, and you are asked to get the derivative of a over b. Okay, so what happens is the derivative of a quotient is equal to b derivative of a minus a derivative of b over b squared. Okay, so you try to do it. You try to write down the statement as you hear it so that you could follow. Okay, so for example, if you're going to represent your a and your b as your x and your x plus 1, so what happens now, if in the next step of representing this expression as u is equal to x over x plus 1, then next step is to get the derivative of u, which is the derivative of the quotient x over x plus 1. Now, as what was described earlier, if you the derivative of a quotient, for example, a over b is equal to b derivative of a minus a derivative of b all over b squared. So replacing a and b with x and x plus 1, this serves as your a, x plus 1 serves as your b. Therefore, the derivative of this quotient x over x plus 1 goes like this. This should be x plus 1 derivative of x, which is 1, minus x derivative of x plus 1 is 1 all over x plus 1 square. Simplifying further, this becomes x plus 1 minus x over x plus 1 square. This becomes 1 over x plus 1 square. Okay, so the derivative of x over x plus 1 is actually is the one that appears here. This is x plus 1 minus x over x plus 1 square. This is actually the derivative of x over x plus 1. Now, why is it that there appears here 1 over x over x plus 1? It is because what we want to do is to make things simpler. We just represent the quotient x over x plus 1 as u. So remember, the step goes, let u equal to x over x plus 1, then get the derivative of u. Now, if you replace x over x plus 1 as u, the derivative of ln u is 1 over u derivative of u. Remember, in our expression, derivative of ln of x is dx over x. If you replace x with u, derivative of ln u is du over u. Now, applying this directly to this expression, our u here is this quotient, so ln of u, derivative of ln of u is ln of u, derivative of u. Okay, let me repeat that. Ln of u, the derivative of ln of u is 1 over u, so 1 over u, derivative of u. So this is actually 1 over u times derivative of u. Okay, so I hope you get that. Now, although it is shown here in this example that the module does not directly make the representation of the transition between u and the given expression x over x plus 1, what you need to do in order to follow is to follow the instructions here in the video lecture using your pens and paper in order to follow the computation presented here. So let me repeat that again. The first step in order to get the derivative from this expression to eventually get the answer is first let u equal to x over x plus 1. Once you represent x over x plus 1 as u, the next step is to get the derivative of u. Now, the derivative of u is the derivative of x over x plus 1, meaning you need to get the derivative of the quotient x over x plus 1. And the answer for the derivative of the quotient is this one, x plus 1 minus x over x plus 1 square. Okay, so how did we arrive with this x plus 1 minus x over x plus 1 square? This is the result of the derivative of a quotient, so you need to review from your differential calculus the process of doing or performing the derivative of a quotient. Okay, so going back, now we represented this as u, so what happens here is this becomes ln of u. Now, getting the derivative of ln of u, the derivative of ln of u is ln is 1 over u derivative of u. So 1 over u times the derivative of u. Now, once you have done this, once you have done this process, the next step is simply to simplify using algebraic manipulations. Of course, what happens here is that this is division of fraction. So you have 1 over x plus 1 becomes x plus 1 over x. And of course, in this numerator, x minus x becomes 0, and what is left here is 1 over x plus 1 square. Now, x plus 1 here is an expression that can be cancelled by one of the x plus 1 in this denominator. So what happens is that you cancel one of the terms x plus 1, so what is left here is the other factor x plus 1. So what is left is 1 over x times x plus 1. Now remember, in this part is simply a review of the basic derivatives of the natural logarithmic function and the exponential function. Later on, we will be reversing this process using integrals, so it is worth noting, or it is worth reviewing this portion in your previous course on differential calculus. Okay, so next, number 2, we have e raised to x plus 5 raised to x. Okay, so in order to perform the derivative for e raised to x plus 5 raised to x, what we need just to do is to recall the process of getting the derivative for e raised to x and getting the derivative of the form of 5 raised to x, or a constant raised to x. Okay, so for that portion, let us recall from your differential calculus that the derivative of e raised to x is e raised to x derivative of x. Also, the derivative of a raised to x, where a is a constant, is equal to a raised to x ln of a derivative of x. Now, if you're having difficulty, in recalling these formulas for getting the derivative, you need to review these things from your differential calculus. Okay, so let's proceed. Now, this term is composed of a sum of terms, so therefore, if you're going to get the derivative of these two, we simply distribute the process of getting the derivative for both terms. This means that we're going to get simply the derivative of e raised to x plus the derivative of 5 raised to x. Okay, so of course, the derivative of e raised to x is e raised to x derivative of x, plus the derivative of 5 raised to x is 5 raised to x ln of 5. Just as we recall in the formulas for getting the derivatives. Now, probably at this point you're wondering, why is it that the derivative of ln of x is dx over x? Why is it that the derivative of e raised to x is e raised to x derivative of x? And probably also for the third formula, that the derivative of a raised to x is a raised to x ln of a. These things are verifiable if you're going to Google it, for example, trying to look for the proof for the equivalency of this process of getting the derivative, for example, for ln of x. Why is it that it is equal to dx over x? But if you're going to ask me for the proof, I could also provide the proof for you, but it would be I was not able to prepare that. I'll be preparing that in a separate discussion, primarily because these are derivatives and supposed to be at this point. We are supposed to be done with. You are supposed to be done with these topics, and we are actually on the second half of your study in calculus. So this is integral. So what I am expecting that you already know, or perhaps you would research on it on your own, and that is why I left it as a burden on your part of recalling these basic concepts. But again, if you're going to, for example, request for the proof, perhaps I'll be giving it some time to write it down in this form of the in Word format form, so that I could provide it to you. But in any case, this the proofs for this results are actually verifiable if you're going to Google it or search on it on the internet. Okay, so let's proceed now with the third example, 2 raised to cosine x. Okay, so first step in doing this is to let u equal to cosine x. Of course, the next step is to get the derivative of u. The derivative of u is the derivative of cosine. The derivative of cosine is negative sine x. Okay, so representing the original cosine x as u, our original expression 2 raised to cosine x becomes 2 raised to u. Then we get the derivative of 2 raised to u. Now, of course, the derivative of 2 raised to u is of the form a raised to x, just like what we see here. So therefore, the result of a raised to x is a raised to x ln of a. Therefore, if we have instead as a raised to x equal to 2 raised to u, therefore this becomes 2 raised to u ln of 2. Now, notice that this is wrong. This is supposed to be 2 raised to u, not 2 times u. So this is supposed to be 2 raised to u ln of 2. Now, the next step is the next step that appears here is the replacement of the representation of u to its original representation as cosine x. So notice that it is 2 raised to cosine x, 2 raised to cosine x, proving that this is actually a typographical error. This is supposed to be 2 raised to u. So this becomes 2 raised to cosine x ln of 2 times the derivative of x, which is the derivative of u, which is negative sine x. So overall, this becomes negative 2 cosine x ln of 2 sine x. Okay, so I'll be leaving you the simply a flash of the next examples, number 4, number 5, and so on. There are actually 10 examples here that you could verify on your own and try to do them as part of the of your own practice exercises. But I am not requiring you to pass this simply because you already seen the solution. So the idea is simply for you to practice the individual steps of getting the in doing the process. So I'll be flashing them one by one, giving it a few seconds so that you could somehow record the items. Perhaps if you have your cell phone cameras, you could take a picture of the no, of the screen, or perhaps you could get a screenshot of the screen on your computer so that you could record the items here. Okay, so this is number 4, number 5, number 6, and number 7. Number 8 and number 9. And finally, number 10. What you could do is to print screen your screen, then perhaps you paste it on a Word document so that you could record the result. Again, I'm not asking you to submit the result because you already seen the solution. What I'm asking you is for your own practice exercises so that you could practice how the solution works, is for you to practice the solution on your own and try to understand how the steps have gone from one step to the next. Okay, so for as of this topic, I will now be discussing some of the um, techniques of integration of transcendental functions.